All right, so we've talked about solvating ions in water. So ionic substances in a polar solution, or a polar solute. I'm sorry, solvent. Ions are solute, water is the solvent. Now we've just recently talked about how we dissolve a polar substance like a sugar in water, which is a polar substance, so polar and polar. So what I want to talk about next is how you dissolve nonpolar things in nonpolar things. Okay? Particle interactions are always the result of polar attractions of some kind. Okay? Sodium ions are attracted to, let's back it up a minute. Attractions are always the result. You're dissolving anything because of opposite charges, whether they're small or big. Okay? For dissolving something ionic, those attractions are due to opposite charges. Okay? If we're dissolving something that's polar, the attractions are due to the opposite charges. So if we have a nonpolar thing, in our last unit, we described what happens with nonpolar as a shift in electron density. So the electrons are constantly moving around here at really, really high rates of speed. So statistically, if we were to freeze everything at one instant, the electrons are never going to be balanced, and they almost never. They occasionally are, but very rarely. Most of the time, you're going to have an uneven arrangement because they're moving randomly. They're moving in all kinds of directions. And so you're going to have periodically, and more often than not, a temporary shift in electron density, creating a positive and negative end of that molecule. But remember, it's only temporary. Not like polar, which is permanent. It's temporary. Okay? It's temporary. Right, Zach? Right, Ben? Right, Chelsea? Maurice? Yes, sir. Oh, Dev? Right, Dev? Right, Dev? Hey, Dev, how about think with your head up off your desk, okay? Thanks. All right, so when we have a temporary polarity. This is much weaker. This is much weaker as a result. So we have a temporary shift in electron density. We still have attractions between partially positive and negative ends. I'm sorry, I got that backwards, don't I? This should be negative over here, and this should be positive. So those are attracted to each other. All right? But because it's temporary, it's much weaker. It's temporary, so it's weaker. Polar attractions, permanently polar attractions, are much stronger. Those are called dipole-dipole. Ionic attractions are stronger still because those are permanently, completely charged particles. But this is a temporary attraction. So, if I have something like propane, that's a 2, and gasoline, which is largely octane, okay, this is all nonpolar stuff. So the attraction between this molecule and this molecule is all due to those temporary shifts in electron density. Okay? Regardless, if gasoline is the solvent, and usually we use gasoline as the solvent, if we want to dissolve some propane in gasoline, they're just simply going to have propane molecules surrounded by these gasoline molecules because of this shift in electron density. Okay?
What is that?
Like a flower.
Oh yeah, I kind of made a flower out of it, didn't I?
What is that?
Flower.
Propane, gasoline.
Oh.
Yeah, you put too long on the first.
Wait, is this cup
That doesn't matter.
Oh.
It's just a kind of a little bit of a chemistry joke. Okay? Chemistry humor. We got to get our jolly somewhere, right? Okay. Now, why is it then that something like water, which is highly polar, and something like oil or propane, which is nonpolar, why can't water dissolve the nonpolar stuff, or vice versa? Why don't they like each other? Okay? Well, the nonpolar stuff likes the water okay. The water doesn't like the nonpolar stuff. Water, because it is so strongly polar and so strongly attracted to other water molecules through hydrogen bonding, that it basically pushes out the nonpolar stuff. Water's cliquish. Okay? It pushes out the nonpolar stuff. Alright? So it's not that oil won't dissolve water, it's that water refuses to dissolve in oil. Does that make sense? Huh? Okay. Remember, the nonpolar stuff is attracted to other nonpolar stuff through these weak attractions, right? Weak, temporary shifts in electron density attractions, London forces. Water molecules are attracted to this really much stronger, permanently polar attraction, hydrogen bonding actually. This is so strong, it pushes this stuff out. That makes sense? So water is cliquish. You know, they kind of like, you know, they're talking to each other, but they don't let somebody else get involved. Okay? Got that? That makes sense? Okay? So, it's always some kind of polarity involved in dissolution, in dissolving. But it's different kinds of processes. The solvation process is different for different kinds of solutes and solvents. The solvation process is different for different kinds of solutes and solvents. Right, Zachary? Chelsea? Andrew? Well, his head was down for a second there. He's drifting off on me over there. Okay? Ben?
Calling y'all out on camera.
Yeah, on video, on the recording. So if your mama's listening, she knows. Okay. Why don't we all stand up and stretch a minute? Let's all stand up and stretch a minute.